Good morning and good afternoon. My name is Joe Rogers, and I work in business development for the Clinical Oncology Next Generation Sequencing Division at Thermo Fisher Scientific. On behalf of Thermo Fisher Scientific and my colleagues who develop and support the NGS-based tools for improved oncology profiling, I would like to welcome you to our educational program entitled Changing the Precision Oncology Research Paradigm. Today's event is intended to provide attendees with a high-level understanding of the decision-making process in bringing NGS-based oncology testing in-house from a pathologist and administrative perspective, as well as give you an insightful view on the ease of use and overall effectiveness of the Genexus platform to accomplish this goal. I want to thank you all in attendance for your time today, and would you please complete the poll at the conclusion of the presentations. With that, I would like to introduce Dr. Eric Vail to discuss the importance of getting clinical research results as fast as possible, impact of QNS, and related case studies. Dr. Vail is currently the Director of Molecular Pathology at Cedars-Sinai Medical Center, responsible for the administration, development, and validation of all clinical molecular diagnostics at Cedars-Sinai. Dr. Vail received his MD from St. George's University. In 2017, he completed his APCP residency at New York Medical College and subsequently finished a molecular genetic pathology fellowship at Cedars-Sinai. Dr. Vail's primary research focus is in the utilization of clinical resequencing in cancer, and more recently, the local genomics of SARS-CoV-2. Dr. Vail, thank you very much for joining us.
Hey, good morning, everybody. My name is Eric Vail. I am the Director of Molecular Pathology here at Cedars-Sinai Medical Center. And before COVID, I actually did a lot of oncology. Just a quick disclosure, Thermo Fisher and its affiliates don't employ me. They're not endorsing anything that we're saying here. And I was not providing any, I was provided a monetary remuneration for this presentation. I just give a quick outline of what we're going to talk about today. Is sort of the benefits of clinical next generation sequencing and some of the drawbacks. With the ever expanding rise in biomarkers, we're seeing really a need to do more testing on more people. So I really want to see how important this is. This chart is not completely perfect because clinically relevant biomarkers actually in oncology started in the mid-'80s with hormone receptors in breast cancer and selective estrogen receptor modulators. But we generally think of the era of precision medicine starting a little later than that with HER2 in breast cancer in 1998 and in BCR-ABL in CML when everybody thought we cured cancer forever, and it just ended up turning out to be a lot more difficult than we ended up predicting in the beginning. There was a little bit of a delay from then into the late 2000s where EGFR and ALK started coming out, and then with lung cancer really leading the way, the last 5 years have been an explosion of different biomarkers and approvals. This is a relatively recent graph, but even it's outdated because of how quickly things are moving. We have RET and MET already approved as well. Other tumor types are really starting to come into the fore with things like homologous recombination genes being important for PARP inhibitors in multiple different tumor types, PIK3CA in breast cancer, NTRK, MSI being biomarkers that are pan-tumor now. So now it's not just which tumor type and which biomarker, but you're having these biomarkers that can also be for multiple different tumor types across the board. So I think the next kind of thing that's important is that a lot of these biomarkers are relatively rare, and as we start discovering more and more of them, as we start getting more and more indications, we're going to be starting to cut smaller and smaller pieces of the pie off. And so you're getting situations where things like NTRK, where sub 0.1% pan tumor, and it is exceptionally difficult to do that in a way that's efficient unless you're doing something like sequencing. So in the past, most biomarkers were detected by single gene assays. These were, your IHC, your FISH, your allele-specific PCR. They're great tests. They do an amazing job for what they do. They're highly specific, but in general, they provide limited information. Of course, they're just a single gene test, right? And as we move away from 1, 2 biomarkers in a tumor, we're finding that you need to do more and more and more of these tests to be able to have a complete analysis. This increased amount of tests, now all of a sudden these cheap, relatively tissue-sparing assays start to become a burden. You need 5, 6, 7, 8 tests now for lung cancer if you're going to do everything that's recommended in a single gene fashion, and this increases costs obviously and tissue requirements as well in an era where we're having smaller and smaller and smaller tissue. This is where sequencing comes in. So next generation sequencing, I think the better name for it is massively parallel sequencing. It's much more descriptive. It actually says what it does. It's basically you're sequencing huge amounts of genetic material all in parallel, all at the same time. And for the amount of information that you're receiving, it is exceptionally cheap. Everyone's seen that graph, essentially, of the cost per base as it shoots down. And for what you get again, it's much quicker as well. The Human Genome Project, which cost trillions and was took years and years and years, and we're talking about a whole genome in less than a week. And actually, if you're a sick infant, there's protocols to get a genome done in a day, and to have it relatively cheaply as well. Sequencing is available commercially and clinically for over a decade. Almost, I think, 2006, 2007. So it's in the beginning there were issues and a lot of technical expertise that was required in things like informatics, in the wet lab, that was really hard for the broader community to be able to adapt. Most of those have been significantly improved on over time. The technology is incredibly reliable, and there's plenty of commercial applications and commercial kits that are available for people to use on their own. The technical costs which used to be astronomical, are now less than the analytical costs most of the time, especially if you're doing any sort of clinical sequencing. And it really depends on the panel size. Because the more amount of stuff that you're looking at, the more amount of variance you're going to get that you might not know what they are. We have 161 gene panel, the gene list to the right, that we currently run for our solid tumor assay, and this, I guess, would be considered a medium-sized panel for solid tumor testing. We're thinking of moving to a 400, 500, 600 gene panel currently, and it just, at a certain point, you start getting more and more of these things that are difficult to analyze. So some of the barriers to NGS testing and the ability to adopt it that we're going to talk about today are long turnaround time, limited tissue, high QNS rate, staffing constraints, and high cost. So turnaround time, I think, is a critical one because of the way that the clinical practice works around cancer patients and what the standard of care is in the first line. Usually, oncologists schedule patients about 2 weeks after they had their procedure to talk with them about what their diagnosis is, what their treatment course will be, what their prognosis, and all that sort of stuff like that. At that point in time, if biomarkers are going to be used in a first-line therapy, they need to be out. And they need to be out in a way that the oncologist understands them and can use them. The problem is that sequencing is one of the longest turnaround time tests of any tests in the laboratory. Instead of being measured in hours or possibly a day, sequencing is often measured in days, weeks, and used to be even in months. Right now, clinical sequencing in oncology is about a week to 3 weeks, and often is measured from receipt in laboratory. So if you're sending out to a large reference laboratory, the oncologist orders, the order goes to the laboratory, then they have to request, and another week goes by before they even get the tissue. So you add that on top of that. Critically, if the patient was an inpatient, because of the vagaries of the American Medicare and how it works, there's a 14-day rule that causes, if you do this testing quickly, to fall under the DRG, where basically the lab has to eat the costs as well. And so if you wait for that 14-day rule to be up, then you send out, then there's another 14 days for it to be resulted. You're talking about 1-2 months before that patient has that data. In many tumor types right now, that is not as critical because it's not being used in the first-line therapy. But in things like lung, colon, breast, these things are becoming more and more important, and we'll be seeing these actually become more and more important across tumors as more of these biomarkers get approved for therapy. So the ability to do really quick, relatively broad sequencing, even single-day turnaround time, promises to alleviate many of these issues. Now you're not really worrying about that 14-day rule anymore because you can just go out, wait for that 14 days, and then have that result out. Either that's the next day or even the same day. This is one of those things that I think that in the near future, and something that we're going to be talking about later in some of these presentations, is going to be a real game changer in how we do this sequencing testing. QNS rates. So while having fallen, it used to be really high. QNS rates are an important consideration in any assay. Almost all of the big reference laboratory panels, so your big 500-600 gene panels that are sent out by oncologists in the community, are using a hybrid capture-based approach. While capture probes have gotten more efficient and the tissue requirements have gone down, QNS rates at these laboratories are still in the 15 to 25% range. These assays require 50, 100 nanograms of nucleic acid. If they're doing DNA and RNA, they require about the same amount of both. If you use a different type of chemistry, if you use what we use in our laboratory, which is an amplicon-based library preparation, there are some downsides to that, including some of the way that the data comes out. But what it does, it allows you to go quicker, and it allows you to have a significantly lower QNS rate. So right now, our QNS rate last year at Cedars was 2.7%, and our assay is listed as requiring 20 nanograms of nucleic acid. We often go down as low as 10, and we've seen results in some of our prior platforms and amplicon-based platforms down as low as 1 nanogram of input nucleic acid that actually produce a result that had actionable findings. I'm not saying that you're going to be able to reproduce this time after time, but on occasion, you will be able to get down that low with amplicon-based chemistry. Staffing is a huge one. Now, so I had staffing and costs kind of together, and I kind of separated them out because they're two different problems. Staffing really comes down to the fact that manual NGS preparation is incredibly time-consuming and skilled. Already there's a national CLS shortage across the country. Most programs that do CLS training only have about 2 to 3 weeks of molecular training, if any. The vast majority of their training is in micro or in core lab or transfusion medicine, but the molecular training is really quite lacking. And so when we end up hiring somebody, we spend 6 months really going over all of the different training, and it can even drag out even longer than that. You can buy liquid handlers, but those are expensive. They usually require high volume to be at their best efficiency. So if you have low volume, it's not really not worth it. And you need expertise in programming as well on many of them to use them to their fullest potential. Use them to the ability to do everything that you want with as little tech intervention as possible. So if there are systems out there that can decrease the total amount of tech time, that can increase the amount of automation without requiring expertise in programming or really high specimen throughput, these are things that are of huge value in any laboratory. And we currently have sort of the gamut of that. So we have automation that's good for high throughput. We have automation that's good for lower throughput, and almost all of it is essentially walk away right now. Cost, and this is a big one. Everyone thinks of a sequencing laboratory as the big black hole of the. First of all, hospitals already think of laboratories as cost centers, and then the laboratory thinks of the sequencing lab as an even bigger cost center. But reimbursement is changing. The landscape has been moving progressively better year after year. Things like lung cancer are reimbursing almost universally at this point for us. And so, at scale, if you're doing volumes approaching ours or even higher than that, the costs per test can be actually really low. But this requires large batches, expensive bulky automation, and importantly, it requires the thousands of cases a year, right? So if you're a medium-sized or a small-sized hospital system that has a costly send-out for sequencing right now, but doesn't have enough samples to be able to run your own sequencing in-house, it's kind of this weird middle zone. And so assays that have the ability to do low batch sizes can have huge amounts of benefit. So I'm talking about 1 to 4 samples per run, but they're currently right now really expensive. This is ideal for lower volume tests that are still costly to send out. This is in our case, we actually don't do that much ctDNA. We're only even in the system, it's only a few a week. And so it's been difficult to justify for us to bring this in-house. And so some of the newer platforms that have the ability to do this low batch size at a more efficient rate, this is the stuff that we're going to be bringing on to be able to do these lower volume tests. I think that it's important because, again, the scenario that I always end up thinking about is as a hospital that has like 3 or 4 lung cancers a week, and they're being nickeled and dimed to get, they're sending out an ALK, they're sending out a ROS, they're sending out a BRAF, they're sending out an EGFR, they're sending out all this testing, and they're paying for it at client bill prices, right? And when you add all of that up, that cost, once you get past 2, 3 different single gene assays, the efficiency of doing sequencing starts to pass it. And if you have also that efficiency at the ability to do low batch sizes, I think that being able to bring that and internalize that in-house is something that's a huge value, not just monetarily for the hospital, but clinically for the patients within it. So the reason I say clinically it's important to do sequencing, and clinically is this sort of case study that I'm going to end with here. This was a 49-year-old man with metastatic bone and brain non-small cell lung cancer. He had a biopsy done at an outside hospital that was doing exactly what I'm saying. They have relatively small volume, and so they send out all of their single gene testing, and he had EGFR Sanger done, a BRAF PCR, a PD-L1 IHC that was done, and then when they got to ALK and ROS for FISH, the sample was QNS. There was nothing left. And so the oncologist had the patient come to Cedars for treatment, and they actually did a repeat biopsy because the ALK and ROS FISH was QNS. And we did sequencing on it, as we do on all of our lung cancer cases. And what we found was not an ALK or ROS rearrangement. We actually ended up finding a rare variant inside of EGFR that was not covered by the Sanger sequencing. So this is an EGFR kinase domain duplication. Essentially what it is the kinase domain, so exons 18 to 25 of the EGFR gene were duplicated. It's an activating mutation. It's relatively rare. Some studies said it's about 1% of all EGFR mutations, so say 1% of 15%, right, of non-small cell lung cancer. But I bet you that number is actually a little higher because we haven't been testing for it. And we'll probably see that rise over time. Importantly, it's targetable. There were papers at the time that were showing some sensitivity to TKI therapy, afatinib. We actually ended up having the patient on the third generation TKI, osimertinib, and they did amazingly. Their tumor melted. This is now 2 years now, and this is one of those things that would have never been found if this patient had single gene testing only. Only sequencing will pick up something like this, and the reason is because it's not designed. The single gene tests for EGFR are not designed to be able to pick up these sort of rearrangements, and they can't be asked to because it's so rare. Sequencing has the ability to include essentially every single rare variant along with all of the common ones for only a fraction, slightly higher cost. So I think that understanding that you can have a cost-efficient molecular laboratory that is also clinically beneficial to patients in 2020 is something that can be done now with some of the new technologies coming out. So these are some of the future improvements that I think a lot of pathologists want to see before they bring in sequencing in-house. They want to see the ability to have reduced turnaround time so that their testing can be worked around, so something like the 14-day rule, or their testing can get out relatively quickly. Batching flexibility is huge. This actually ends up helping with turnaround time, because now instead of waiting 2 weeks to fill up a big batch, you can run something every day or every other day or as soon as you get a sample. Before, when this would be cost prohibitive, if you have new technologies that bring it down, this becomes something that's reasonable now. And then finally, I think everybody wants a simplified laboratory workflow. We have consolidated almost all, by doing sequencing, you end up consolidating all of your single gene tests into those sequencing panels. You don't need to have 10 different QCs. You don't need to have all the different CAP checklists, all the different proficiencies for all your techs. It's something that really ends up being beneficial for the lab overall and provides cost savings that aren't even seen when you first look at it. So with that, I will take any questions. Thank you.
Thank you, Dr. Vail, for your time and presentation today. It looks like we didn't have any questions come in, but we really appreciate your information. It was a great perspective from the pathologist's point of view. Now to discuss the new world of easy NGS with the Genexus system, I would like to introduce our next speaker, Dr. Andy Felton. Dr. Felton will provide an overview of the Genexus system and the benefits of using the platform after SARS-CoV-2 with minimal hands-on time and reduced and/or furloughed lab staff. Andy is currently the Vice President of Product Management and Market Development for the Clinical Sequencing Division, responsible for the development and launch of all products related to ion-torn NGS systems. Andy began his career at Applied Biosystems UK team in 1994 after completing an undergraduate degree in chemistry at Liverpool University, and his PhD focused on peptide fragments and epidermal growth factor at Oxford Brookes University. In 1997, he moved to corporate headquarters in California and entered product management. During this time, Andy was responsible for a number of product lines and launches, including the launch of the 7300, 7500, and 7500 fast real-time PCR systems, the 3500 and 3500DX genetic analyzers, and eventually becoming the director of capillary electrophoresis business. Andy joined Ion Torrent in June 2010 during its startup phase and subsequent purchase by Life Technologies. Andy, thank you very much for joining us today.
Well, welcome to the presentation, and thank you very much for joining. My name is Andy Felton, and today I'm going to be talking about the Ion Torrent Genexus system, really the first specimen to report turnkey next-generation sequencing platform. Just a quick safe harbor statement. Genexus system and its assays for research use only. The content of this presentation is based on future potential developments and is intended to be entirely future-looking in nature. Thermo Fisher Scientific is not promoting or encouraging any current diagnostic or clinical use of the Genexus system or any other research use only products discussed in this presentation. So the challenges and barriers today are really shown on this slide in terms of how to implement next generation sequencing in the clinical research setting. Quite often it's a very slow and complex operation. Results can take days to weeks to be turned around. There's generally been a high level expertise required to run NGS, and it's often been the case that many modular workflows and multiple instrument systems are required to generate the data. And lastly, in terms of the economics and the actual tissue requirements for the sample, in general, it's been quite difficult for staff to maintain their training and hire, and also be able to economically run the right batch numbers of samples, in particular for a smaller number of samples that labs may often get in the door in a week. And many of the samples that come through the door typically have very small quantities of material available to them. And with those very small quantities of material become quantity not sufficient problems. In other words, there isn't enough sample to generate an actual result. What we've been developing over the last few years is a system that aims to solve the majority, if not all, of those problems. So called the Genexus system, as I mentioned, it's the world's first, we believe, turnkey, fully automated next-generation sequencing platform that allows you to process from the biological specimen and generate a report in a single day with just 2 user touch points. And the aim of this system is really to allow you to generate next-generation sequencing or mutational profiling results at the same time as your immunohistochemistry result and provide the maximum amount of information to your clients in terms of the data on the mutational profile of the sample. The system consists of both automated sample preparation, and that's the box, the smaller box on the left-hand side. And then on the right-hand side is a single, what we call integrated sequencer that contains library prep, sequencing, and analysis, as well as reporting to deliver results in that single day. It allows you to economically batch the samples and is built with the requirements of FDA registration in the future and ISO 1345 requirements for both the system and the consumables. And today, what we're going to talk mainly about is oncology applications, but we have validated both inherited molecular genetic testing data, as well as reproductive health and some infectious disease assays as well. So here's an overview of the system. As I mentioned, on the left-hand side is what's called the Ion Torrent Genexus purification system. That's currently in development and available in the early part of 2021. And into that, you place your lysates in the case of an FFPE sample. So there's some offline preparation work to generate a lysate from the FFP sample. Or you place plasma directly in for a liquid biopsy application, or any one of the sample types you see there. In about 4 hours for up to 12 FFPE samples, You can prepare both the isolated DNA and RNA, or you can run up to 6 4 ml plasma samples through the system. The purification system will output both a working plate of quantitated nucleic acid, so it fully automates the extraction process with cartridge-based reagents and simple, easy-to-use setup of about 5 minutes, and then outputs both a working plate of quantitative nucleic acid and, in the case of FFP, an archival plate which you can retain for future use. That working plate then goes into the next part of the workflow, again with a simple 5 minutes of hands-on setup time, into the Ion Torrent Genexus integrated sequencer, which performs the steps of library preparation, clonal amplification, sequencing, and reporting. And what you can see there are the number of elements. The chip itself is brand new on this platform. It uses our standard ion semiconductor sequencing chemistries. But the chip in this case is broken up into 4 lanes, and each lane has 12 to 15 million reads, and each lane can be addressed independently. So in the case of this chip, you can see it's about 12 hours for a single lane on the chip to be run, and depending on which exact protocol you run, between 18 and up to about 36 hours, with the majority of applications running in less than 24 hours on a full chip. In terms of the number of samples that can be prepared, the capability of the system is up to 32 libraries per run, and I'll break down in the next slide how that will interface with the number of samples that we can run, but 32 libraries is the max that can be generated in a single run. So it really helps to flexibly utilize your workflow, and in that up to 4 different kinds of assays can be prepared and sequenced simultaneously in a single run. That's provided they run on the same chemistry or have compatible thermal protocols. And as I said, about 32, maximum of 32 library preparations in a single run. The chemistries that we support for library preparation are our current AmpliSeq protocols and our AmpliSeq HB-based protocols. And that covers the vast majority of our portfolio of assays, both in oncology, inherited disease, and infectious disease. The majority of them are based on either AmpliSeq or HD. In terms of the number of samples, that breaks down the following way. So if you have a single pool Amplicon library for AmpliSeq or AmpliSeq HD, you can actually run up to 32 samples. If you require a 2-pool library, then you would be able to run 16 samples or an 8-pool for 4. The beauty of the system is that the chip and the reagents can stay on the instrument for up to 2 weeks. So, for example, if you want to run a few samples in week 1, you might choose to use lane 1 or lane 1 plus 2, and then come back the following week and then use up lanes 3 and 4. Or every other day, you might be using a lane, depending on how your samples come into the lab. So the throughput and assay flexibility is really maintained by having both the chip and strips of reagents which correspond to the numbers of samples that you are coming into the lab in any particular time frame. In terms of the numbers of samples that could be run, what you can see on this chart for a particular assay type, so let's pick about the 4th assay down, the Oncomine precision assay, total nucleic acid. So this would be a liquid biopsy workflow. You can see for a liquid biopsy sample, we can run 1 sample per lane. So the chip can run up to a total of 4 samples per chip. Whereas if you take that same Oncomine precision assay and run it for FFP samples, the depth of sequencing requirement isn't nearly as high. So you can run 4 samples on a lane or a total of 16 samples on a chip. And there are various assays that you see there that we have worked out both the sample numbers and the turnaround time for. So looking at the bottom row of the table, the turnaround time for Oncomine precision assay for the CFTNA or total nucleic acid liquid biopsy workflow is 14 hours for a single lane or 18 hours for a 4 sample run. And correspondingly for the FFPE, that would be 14.5 hours for a single lane of samples for 4 samples, and just over a day at 27 hours for 16 samples in a row. In terms of generating the final output and the final reporting, there are really three pretty simple steps. Genexus software automatically generates a table of variants, and these variants are then filtered and reviewed, and that takes about a minute. It takes about a minute to QC the samples. And then we go on to generate a report, and that takes about 5 minutes. This is what a report looks like. So end-to-end integration from specimen to report. On the right-hand side, you can see the example of a particular output from a non-small cell lung cancer FFPE sample. And you can see we are detecting in this particular case a RET fusion as well as a PIK3CA mutation. So it's a very simple report. You can have it as a single-page report with all the findings summarized to make it very easy to use, or a more complex report, and it is customizable depending on the lab's needs. We have option for integrated analysis on the instrument, or you can use our cloud Ion Reporter version or a separate Ion Reporter server. Genexus 6.2 software, which is our latest revision, contains some really fantastic features, allowing you to, for example, here, compare variant reports across samples or across time. In this case, you can see that a particular sample was queried for variants, and you can see the frequency of those variants is varying depending on the time a sample was collected. So we can see the progress of the therapy as it works on the sample over time. So lastly, I'll give you some examples of our customers who've been using the data, and you're hopefully going to hear more through this presentation. This is a set of research from our collaborator and now colleague, Dr. Jose Luis Costa, when he was at the Institute of Molecular Pathology at the University of Porto in Portugal. And he was comparing samples between run on his existing GeneStudio platform and his Genexus platform, and showing both the uniformity of coverage, the percent of reads on target, and the amplicon coverage. So some basic metrics in terms of the performance of amplicon-based sequencing on either the GeneStudio or Genexus platform. In this case, it was a postnatal and prenatal research samples for inherited disease AmpliSeq-based panel, and you can see the comparable performance between the two. And if you want to look at that presentation in more detail, there's a link on the slide. Secondly, we ran a multi-center study coordinated by Dr. Michael Hummel from the Charity Institute of Medicine in Berlin. And you can see the results on the right-hand slide. So in this case, we were comparing multiple FFPE samples for concordance between with Genexus and Oncomine precision assay against previously characterized samples using a variety of different assays, the Oncomine Focus, the Oncomine Solid Tumor, colon and lung V2, and also the Illumina TrueSight 170. And the graph shows you that we have a very high R-squared, or correlation, between the data on all those different assays versus the Oncomine precision assay. And we have both high sensitivity and specificity, as well as high concordance for those assays on the Genexus using the Oncomine precision assay. An example of some data from one of our collaborators at the University of Basel in Switzerland, Dr. Philip German. And in this case, we were detecting an ALK fusion with a novel technology that's built into the Oncomine precision assay that's called Fusion Sync, and this allows us to detect novel fusions. And if you look at the little graph on the right, you can see on the y-axis the exon, and the blue line indicates the reads related to the particular fusion event, and the gray bars are the comparable if there were no fusion present. So you can see here at above exon 15, or below exon 15, we're seeing a significant reduction in the number of reads we see. And above that, you can see the reads go back to normal. So we're detecting an ALK fusion via this novel imbalance method, and then concordant to an ALK break-apart fish experiment. And lastly, Dr. Amanda Lowe from the Japan Center for Cancer Research, or Foundation for Cancer Research, compared our Genexus Oncomine precision assay against, in liquid biopsy mode, against previously characterized mutations, so newly diagnosed with EGFR mutations or after therapy on progressive disease after treatment with EGFR TKI inhibitors. And you can see we have 100% concordance in the detection of those mutations and the kinds of mutations relative to the previous data. So really great to see how concordant that sample set is. We expect to keep continuing the assay development roadmap through this year and into next year, adding additional targets. We've already launched our SARS-CoV-2 assay for whole genome resequencing on the Genexus platform. We have just announced our myeloid assay on the Genexus platform for hemato-oncology. We expect to add a BRCA, Oncomine BRCA assay around about the end of this year, and we'll be continuing to build out the selection of assays as we go into 2021 and beyond. And we also support custom AmpliSeq or custom AmpliSeq HD assays, as well as our Oncomine comprehensive assay v3, our Oncomine TCR beta long read assay, and our AmpliSeq on-demand portfolio. So already a significant group of assays and technologies on the Genexus platform that will continue to build as we go through 21 and 22. Thank you for your time.
Thank you, Andy, for your time and presentation today. It was a great overview of the Genexus platform and provided excellent insight into its ease of use and utility in precision oncology. I would like to remind the audience they can ask questions in the chat feature, and we do have a few questions that have come in for you, Andy. Question number 1. Our lab has currently taken on SARS-CoV-2 testing, and we have had to hire more techs to keep up with the volumes. Will we need to add additional FTEs to start doing oncology research testing on the Genexus, and if so, how many?
So that's a great question. Thank you, Joe. So the system is designed to be a very low amount of hands-on time for the tech. So we expect about 10 to 20 minutes of actual physical setup time for the instrument, and then some time to prepare the samples. So I would say in most cases, it probably doesn't require an extra pair of hands to actually operate the Genexus instrument, given the amount of low amount of hands-on time to actually get it set up and running, and then it runs completely automatically after that.
Great. Next question. How difficult is it to bring in the Genexus system, and what kind of support does Thermo Fisher provide?
Yeah, that's another great question. Obviously, Thermo Fisher has a pretty extensive support team, both in our field applications scientist group and specifically for oncology, we have a clinical application scientist team. So these are groups of scientists who are trained or have been involved with laboratory test development in their past careers. And they will help you get up and running, and they can help through the process of getting the instrument to lab, answering questions about how you would validate it within your own facility, and then assisting in the process to get the assay up and running. So there's an extensive support team, both on the application side as well as the service side, to get you up and running. We also have field bioinformatics scientists who can answer questions on the data itself.
Great, thank you. And we did have another question come in as you were answering that one. Is OPA testing both RNA and DNA in plasma? If this is the case, how do you stabilize the cell-free RNA in plasma? Or which tubes are currently the best for cell-free DNA and cell-free RNA variants to apply NGS? I hope that made sense.
Yeah, no, that's a very good question. So yes, Oncomine Precision Assay detects both RNA and DNA in plasma. We are detecting gene fusion events. In terms of stabilizing the blood sample itself, usually we recommend if it either an EDTA or a Streck tube. In the case of an EDTA tube, we recommend that the tube is spun down as quickly as possible after draw, and then the sample is run usually within 24 hours. With Streck stabilized tubes, obviously you get a little more time, but generally a quicker is better in most cases. I think that covers the question.
Yeah, great answer. Okay, thank you again, Andy. Appreciate the presentation and the support there on the questions. Now for financial and operational impacts for implementing the Genexus system in your lab, I would like to introduce Mr. Kevin Kawaxchi. Kevin will discuss the ease of use of the instrumentation, specimen to report testing without the need for bioinformatics expertise, minimal hands-on time needed, and financial benefits of bringing NGS in-house. Kevin is currently the Associate Director of the Molecular Pathology and Cytogenetics Laboratories at Cedars-Sinai Medical Center, Department of Pathology and Laboratory Medicine. Kevin has worked at Cedars-Sinai for more than 30 years as a clinical laboratory scientist. He has a specialist certification in immunology from the SAP and received his master's in public health from UCLA. Kevin has been involved with molecular testing for more than 20 years. His current role is to oversee operations and testing in the molecular pathology and cytogenetics laboratories. Kevin, thank you for joining us today.
Hello, I'm Kevin Kawaxchi. I'm the Associate Director of Cytogenetics and Molecular Pathology at Cedars-Sinai Medical Center in Los Angeles. Today I'll be talking about the financial and operational impact of the Genexus for in-house genetic profiling. Here's a standard disclaimer. I'd like to talk a little bit about the Cedars-Sinai Molecular Pathology Laboratory. We are a small to medium-sized molecular pathology hospital laboratory and do approximately 22,000 samples a year, but we have now taken on COVID testing, which has more than quadrupled our volume to close to north of 150,000 samples a year. We do a mixed variety of testing within our molecular laboratory. We do some viral testing, including COVID-2 testing. We do some genetic testing, as well as oncology testing, including both hematologic and solid tumor testing. And we also perform sequencing on both tumor and myeloid samples. We currently are doing on tumor samples approximately 900 samples per year, and myeloid approximately 200 a year. So our volume is close to 1,200 a year, 11 to 1,200 a year in testing, and it continues to increase. So a little bit on the Thermo Fisher Genexus system, and what I'm going to talk a little bit about is what our considerations in the laboratory for acquiring a new piece of instrumentation, or what we consider when we are looking to bring in a test. And the first part will be a little bit on testing availability, what is available on the platform on any individual test, as well as some operational efficiencies. What is it going to bring to the laboratory relative to the operational standpoint, as well as what is the benefit to cost of performing this test, from the perspective of labor or changing and how it's going to change your test menu. And in addition to that, we'd like to look at bioinformatics and, what type of support do you get for instrumentation? I think within the laboratory, that is a big concern. And then just what the overall workflow impact or changes would be in looking at the Genexus system. Okay, so for testing availability, we look at, as we're looking at the Genexus system, we look at, what are the primary considerations for bringing in this instrument? And for us, it was the Oncomine precision assay. And what caught our eye on this assay was the amount of nucleic acid input that is required for this assay, as well as the turnaround time, and as well as the sample types that can be used, both the FFP and circulating tumor DNA. Secondary considerations, obviously, you don't buy an instrument for just one test, is what can we add to our menu in addition to the Oncomine precision assay? And that would be TCR beta as well as a comprehensive, and to that, the myeloid assay. So those are all considerations that we had once for future growth on the instrumentation. So first we'll look at a little bit on operational efficiency. I think just for comparison's sake, I have some things on what we've been doing here at Cedars-Sinai over the past 6 years. And we started out with a 50-gene cancer hotspot panel using the PGM platform. Back when we first started, it was about 14 hours of technologist hands-on time over 2.5 days. A significant amount of time to be used to do the test, but also the challenge of having multiple technologists do this test and getting the consistency that you would be interested in getting on an assay. In 2016, we moved to the 50-gene cancer hotspot panel using the Ion Chef and the S5 sequencer. That was a significant change for us in that we were able to now automate some of the processes and free up a technologist to be able to do other testing and reduce the labor on the tests. So at this point, it was about 3 hours of technologist hands-on time over 2.5 days. And that was the limiting factors back then. What were the number of chefs, and the sequencing time was a little bit longer. In 2018, we brought on the Oncomine comprehensive assay using Ion Chef and the S5 sequencers, and this is about the same 3.5 hours of time hands-on time over about a day and a quarter, about 30 hours. And the game changer here was that we were able to acquire 5 Ion Chefs and 2 S5 primes to be able to perform and optimize the workflow for the assay, being able to create multiple libraries at the same time as well as templating. So this is pretty much the most efficient that we've been. And so when we started to look at the Genexus system, we say, well, what would that change, or what's going to change? And if we can reduce that time with the 3 hours to a third of that, or an hour or less than an hour, that's efficiency that we'd look at. Also, the assay completion time was significantly less than our current assay in 16 to 21 hours. And I think part of in the laboratory world, I believe that scheduling is the most challenging part of performing testing, in that you have to be able to schedule the people, and they also have to have days off. So having a flexible schedule is one of the more important things from the operational efficiency standpoint. Okay, I think I'll talk a little bit about cost analysis, or what goes into the cost evaluation when you get an instrument. And relative to the Genexus, we wanted to take a look at what is single gene testing versus the Oncomine precision assay. And the single gene testing paradigm has been in place for many, many years. And the need for those single genes is very important. And that has been the standard within the laboratory. And the reason for that standard is that there is a need for fast turnaround time for those genes of interest. In able to address this in performing the tests, we think that the Oncomine precision assay on the Genexus may be that solution, in that it can perform testing on a single gene and allow us to not have to run multiple runs of single gene tests per week. Single gene testing also has had a significant impact on the technologist's time and cost for the individual assays, in addition to the higher amount of nucleic acid that is required to do multiple single gene tests. Moving on to an NGS platform and the Oncomine precision assay, this will allow for evaluation of multiple genes simultaneously, and this is the positive aspect of doing sequencing. A turnaround time does vary depending on the size of the platform, the testing that's being done, as well as bioinformatics and the analysis portion of the assay. So by consolidating the gene content, it does reduce the cost per gene relative to doing individual gene testing. Relative to the Oncomine precision assay, we feel that it will show a reduction in labor and turnaround time on the order of single gene testing with an output of multiple genes. So a little bit on bioinformatics and support. Bioinformatics is an area that there is an increasing focus on. Bioinformatics has become as important, if not more important, than the wet bench processes in sequencing. And with bioinformatic pipelines, there's a huge variation in how they are constructed, whether they're built on a standard platform or built in-house, and what variants are called, what annotations are done, and what reports are generated. The appeal for the Genexus system is that it has a consolidated solution while also allowing access of the raw data for evaluation of what the calls are and what calls are made versus what calls that are not made. Relative to support when you purchase an assay or an instrument is probably the most key component. It is important for the success of continued operation to have support from both the vendor as well as on the assay itself. So the advantages to having a unique vendor would be we were able to optimize the assay on the platform with the assistance of the vendor. Also from the perspective of troubleshooting. When there are problems with the assay, if you're not using this compatible vendor or the same vendor, you often run into difficulties in troubleshooting your assay, because it's hard to determine whether it is the assay performance or it's the instrument performance. And I think the most important part is also from the support perspective is what type of service or repair do you get from that vendor? And by having all of these things consolidated on one platform, both the assay and the instrument, it gives us the ability to be able to call and both troubleshoot, and if it is a service-related thing, have somebody come out and fix the instrument as well. So with the Genexus, what impact would it have on the laboratory in the molecular pathology lab? And so what we're seeing is that we're hoping to use this to expand our offerings with a smaller sequencing panel. This would be looked at as a supplement to a larger panel. And as we all know that the panels are increasing in the number of genes, but along with that, we also know that it does increase the turnaround time when you increase the genes. So having the offerings of a smaller sequencing panel really takes us back to what we were doing about 5 or 6 years ago at Cedars-Sinai, in that we took our 50 gene panel and we made even smaller subpanels that were more tailored to certain types of tumors. And so, and the second piece is that the scheduling of the Genexus runs will be flexible. And flexibility, as I said earlier, in the laboratory is key because of staffing is highly variable. Staffing is not 24/7 and 7 days a week. And we have to be able to be flexible and to customize the days that the runs are set up. Having a platform that is fully automated will allow the technologists to have minimal hands-on time, and that is a key component to the Genexus system. Currently, we have to have a technologist available throughout the day, even though the hands-on time may be minimal. They have to be available multiple times a day and multiple sequential days to get the sequencing run completed. Having a flexible batch size is something that also was very interesting for us, in that we would be able to run smaller number of samples and mix the type of samples that we run over a week or 2 week period, allowing us to adjust to the incoming sample volumes. So overall, we think that the Genexus system would be very useful in addition to genetic profiling within the molecular pathology lab at Cedars-Sinai. Thank you. Are there any questions?
Thank you, Kevin, for your time and presentation today. It was a very insightful perspective and important considerations when deciding to bring NGS testing into your lab. And we do have a few questions from the audience. Question number 1. You mentioned that your lab volume quadrupled with the addition of SARS-CoV-2 testing. How will the Genexus workflow fit in with your lab and help your current staffing needs?
So we believe that the Genexus platform will decrease the technologist's hands-on time significantly, allowing us to perform additional testing, including COVID testing. The tech time saved, really is from, preparing the instrument and reagents from both the from library to templating and from templating to sequencing. There is the possibility of saving that tech time and freeing them up to not have to perform testing, at specific times during the day. So this will have a positive impact to the lab.
Great, thank you. Question number 2. Besides being able to interrogate more genes at a time with NGS testing over single gene testing, reducing the cost per gene, what were other financial considerations in deciding to bring in the Genexus?
I believe the versatility of batch size is probably the key thing for the laboratory. Our current sequencing workflow requires a set number of samples per chip, and if you do not reach that set number of samples, the price significantly increases. The Genexus, with the GX5 chip and the 4 lanes, will allow us a little bit more flexibility. Having smaller batch sizes will also allow us to manage our turnaround time a little bit more effectively.
Great, thank you. And thanks again for your time and presentation today. That was definitely helpful information. If we did not get to your question, it will be saved and we will get back to you individually with a response, and the presentation will be available on demand. With that, this concludes our Oncomine Education Day, Changing the Precision Oncology Research Paradigm. I would like to thank Dr. Eric Vail, Dr. Andy Felton, and Mr. Kevin Kawaxchi for sharing their valuable presentations with us today. We would like to thank you all in attendance for your participation in today's program and remind you to please complete the conclusion survey. Thanks again and enjoy the rest of your week.